As humanity gazes deeper into the cosmos, we are confronted with mysteries that challenge our understanding and ignite our imagination. This exploration delves into the inheritance of the universe, guiding us through its expansive history into galactic phenomena, and those tantalizing cosmic signals that hint at life beyond our world. As humanity gazes into the vast expanse of the cosmos, we are filled with an unrelenting curiosity that drives us to explore, to understand, and to challenge the very limits of our knowledge. The universe, in all its grandeur, offers a tapestry of mysteries that continuously redefine our understanding of existence. The concept of the universe's edge, often shrouded in enigma, serves as both a literal and metaphorical boundary, a point where our observational capabilities are stretched to their limits. It is here, at this frontier, that we encounter phenomena such as the cosmic microwave background radiation, CMB, distant galaxies, and gamma-ray bursts, each holding the key to unraveling the secrets of the cosmos. One of the most remarkable discoveries in cosmology is the cosmic microwave background radiation, a faint glow that permeates the universe and serves as a relic of the Big Bang, which occurred approximately 13.8 billion years ago. This radiation, first detected in 1965 by Arno Penzias and Robert Wilson, is a direct remnant of the universe's infancy, providing a snapshot of the cosmos when it was just 380,000 years old. During this epoch, the universe transitioned from an opaque plasma to a transparent state as it cooled and atoms formed, allowing light to travel freely for the first time. The CMB is remarkably uniform, yet it contains tiny fluctuations that reveal the seeds of galaxy formation and the distribution of matter in the early universe. By studying these minute variations, scientists have been able to infer critical details about the universe's composition, age, and rate of expansion. The CMB not only validates the Big Bang theory but also illuminates the journey of the cosmos from a hot, dense state to the vast, structured expanse we observe today. Distant galaxies, visible through powerful telescopes, such as the James Webb Space Telescope and the Hubble Space Telescope, provide another window into the universe's past. When we observe these galaxies, we are looking back in time, often billions of years, due to the finite speed of light. These galaxies, captured in various stages of development, showcase the processes of star formation, stellar evolution, and the gravitational interactions that shaped the universe's large-scale structure. Observations of distant galaxies allow astronomers to piece together the timeline of cosmic history, revealing how stars and stellar systems coalesced from primordial gas clouds under the influence of dark matter and gravity. Each galaxy tells a story, a narrative of formation and growth that spans billions of years, offering insights into the forces that govern the cosmos. Among the most energetic and enigmatic events in the universe are gamma-ray bursts, GRBs. These bursts, first detected in the 1960s by satellites designed to monitor nuclear explosions, are the most powerful explosions known, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. GRBs are believed to originate from cataclysmic events such as the collapse of massive stars into black holes or the collision of neutron stars. These events occur at cosmological distances, often billions of light-years away, yet their brilliance allows them to be observed across vast stretches of space. The study of gamma-ray bursts provides invaluable insights into the extreme physics of the universe, including the behavior of matter and energy under the most intense conditions. By examining the light curves and spectra of GRBs, scientists gain a deeper understanding of stellar evolution, the formation of heavy elements, and the processes that drive the dynamics of the cosmos. The edge of the universe is not a physical boundary but a conceptual one, defined by the limits of our observational reach. It is a region that challenges our imagination and compels us to confront the profound questions of existence. What lies beyond the observable horizon? Is the universe infinite, or does it curve back upon itself in a closed structure? These questions are not merely academic, They speak to the essence of our place in the cosmos. The phenomena observed at the universe's edge, from the faint whispers of the CMB to the luminous beacons of distant galaxies and the fleeting brilliance of gamma-ray bursts, serve as a doorway to understanding the grand tapestry of existence. As we peer into the vastness of the cosmos, we are continuously reminded of the deep interconnectedness that binds all things together. The universe, in its enormity and complexity, is not a collection of isolated phenomena but a unified system where each event, each discovery, and each observation provide a glimpse into the intricate web of existence. The light from distant galaxies, traveling billions of years across the expanse of space, is not simply a beacon illuminating the night sky but a bridge to a time long past, a time when the universe was still young, still full of primordial energy and raw potential, brimming with the possibilities of what it could become. This light, coming to us from the farthest reaches of space, is a direct link to the earliest moments of the universe's history, a reminder of how far we've come and how much there still is to discover. As we look to the future, the exploration of the cosmos holds boundless promise, continuing to reveal new mysteries and inspiring awe as we push the boundaries of our understanding. The universe, vast and ever-expanding, beckons humanity to embark on a journey of discovery that will undoubtedly transform our knowledge of the cosmos. Whether it is through the study of the cosmic microwave background, CMB, the observation of the most distant gamma-ray bursts, or the ongoing search for habitable planets beyond our solar system, we find ourselves at the threshold of uncovering profound truths about the universe's origins, its current state, and its potential future. The CMB, the faint afterglow of the Big Bang, serves as a crucial tool in understanding the early universe. By studying this ancient radiation, scientists gain insights into the conditions that existed just moments after the birth of the cosmos. It provides a snapshot of the universe at a time when it was a mere 380,000 years old, offering clues about its temperature, density, and the distribution of matter that led to the formation of galaxies and other cosmic structures. As technology advances, future studies of the CMB will likely reveal even more about the first moments of the universe, potentially answering questions about its inception and the forces that have shaped its evolution. Similarly, the observation of gamma-ray bursts, the most energetic explosions in the universe, offers a glimpse into always be limited by the tools and theories available to us at any given moment, but the journey of discovery is one that will never truly end. The universe is not a destination but a journey, one that invites us to keep exploring, keep asking questions, and keep dreaming of what lies beyond. Each discovery leads to new questions, and each answer brings us closer to the next great mystery. In this way, the exploration of the cosmos is a never-ending quest, one that reflects the boundless potential of human curiosity and imagination. As we continue our exploration, we are not only expanding our knowledge of the universe, but also discovering more about ourselves and our place in this vast and awe-inspiring cosmos. The light that defines our observable universe carries with it the history of cosmic evolution. As we peer deeper into the cosmos, we are effectively looking back in time, observing celestial objects as they were billions of years ago. This phenomenon allows astronomers to trace the development of galaxies, stars, and other structures, offering insights into the processes that shaped the universe as we know it today. However, the light from regions beyond the observable universe has not yet had enough time to reach us, leaving those areas veiled in profound mystery. Theories about the structure of the universe have sought to unravel this enigma, proposing various models to explain its vastness. Some theories suggest the universe may expand infinitely, with galaxies and cosmic structures continuing endlessly beyond the observable limit. This concept aligns with the idea of a flat universe, where space extends without curvature on a large scale. In contrast, other theories propose that the universe could be curved, much like the surface of a sphere. In this model, traveling in one direction long enough could theoretically bring one back to the starting point, suggesting a finite yet unbounded cosmos. Another possibility is that the universe possesses a saddle-like curvature, creating an open shape where it expands forever but without returning to its origin. Each of these models presents a unique interpretation of the universe's geometry, challenging our understanding of space, time, and infinity. Central to these discussions is the theory of cosmic inflation, a groundbreaking concept introduced in the early 1980s by physicists such as Alan Guth. According to this theory, the universe underwent an unimaginably rapid expansion within the first fraction of a second after the Big Bang. During this brief but explosive period, the universe expanded exponentially, smoothing out irregularities and establishing the large-scale structure we observe today. This inflationary epoch not only explains the uniformity of the cosmic microwave background radiation, CMB, but also provides a framework for understanding why the universe appears flat on large scales. By stretching tiny quantum fluctuations to astronomical proportions, inflation set the stage for the formation of galaxies, clusters, and cosmic filaments that define the universe's intricate web. One of the most intriguing implications of cosmic inflation is the possibility of regions of the universe existing beyond our observational reach. These areas, pushed far away by inflation, may harbor conditions vastly different from those within the observable universe. Such regions could operate under distinct physical laws, governed by variations in fundamental constants. This notion introduces a layer of complexity to the universe's boundaries, suggesting that what we perceive is only a fragment of a much larger and more diverse cosmos. The idea of potentially different regions of the universe with unique physical laws ties into broader discussions about the nature of reality. Could these regions represent alternate versions of the universe, each with its own unique characteristics? This question aligns with the concept of a multiverse, where our universe is just one of countless others, each existing independently within a larger framework. While the multiverse remains a speculative idea, it underscores the profound implications of exploring the universe's boundaries and the mysteries that lie beyond. The observable universe is a testament to the power of human curiosity and the relentless pursuit of knowledge. Through the use of advanced telescopes and cutting-edge technology, astronomers continue to push the limits of our observational capabilities, uncovering new insights into the cosmos. Projects like the James Webb Space Telescope and the Euclid Telescope, designed to investigate the nature of dark energy and dark matter, promise to expand our understanding of the universe's structure and evolution. These efforts not only deepen our comprehension of the observable universe but also inspire us to ponder the vast unknowns that lie beyond. The study of the observable universe highlights the interconnectedness of all cosmic phenomena. From the light of distant galaxies that has traveled billions of years to reach us to the faint echoes of the CMB, every observation contributes to a greater narrative of cosmic history. The boundaries of the observable universe are not just physical limits but also philosophical ones, prompting us to consider the nature of existence and our place within the grand tapestry of the cosmos. As we explore these boundaries, we are reminded that the universe is far more vast, complex, and awe-inspiring than we can currently comprehend. The observable universe is not just a scientific concept, it is a profound reminder of the infinite possibilities that lie beyond the limitations of human perception. Every discovery, from the faint glow of the cosmic microwave background, CMB, to the intricate patterns of distant galaxies, has served to deepen our understanding of the universe, while simultaneously raising new questions that challenge our very understanding of existence. Galaxies, we have been able to track the evolution of cosmic structures over time, learning how galaxies collide, merge, and evolve into the vast collections of stars, gas, and dust that we see in the present day. However, these observations only deepen the mystery. While we have learned much about the formation and evolution of galaxies, we are still uncertain about many of the processes at play. How do galaxies form and maintain their shape? What drives the activity at their centers, where supermassive black holes lie in wait, consuming gas and stars, and in some cases, emitting powerful jets of radiation? These questions, and many others, continue to elude us, pointing to the complexity and unpredictability of the universe's behavior. At the same time, the study of dark matter and dark energy continues to challenge our understanding of the cosmos. Together, dark matter and dark energy make up approximately 95% of the universe's total mass energy content, yet they remain invisible and undetectable by conventional means. Dark matter, though unseen, exerts a gravitational pull on visible matter, affecting the motion of galaxies and clusters of galaxies. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Despite their enormous influence on the structure and evolution of the cosmos, we know almost nothing about the true nature of dark matter and dark energy. Their elusive nature makes them one of the greatest mysteries in modern science, driving researchers to explore new avenues of inquiry in the hopes of unlocking their secrets. As we look toward the future, the observable universe continues to expand, both literally and figuratively. The expansion of the universe itself, which began with the Big Bang, shows no signs of slowing down. In fact, recent observations suggest that the rate of expansion is accelerating, driven by the mysterious force of dark energy. This raises further questions about the ultimate fate of the universe. Will it continue to expand forever, growing colder and more diffuse over time, or will it eventually collapse in on itself in a big crunch? Alternatively, will the expansion slow down, leading to a more stable, long-term cosmic equilibrium? These questions, though profound, remain unanswered, leaving the future of the cosmos shrouded in uncertainty. Despite the incredible progress we have made in understanding the universe, the observable cosmos is, in many ways, still a vast, uncharted wilderness. The further we push the boundaries of our knowledge, the more we realize how much remains beyond our reach. There are realms of the universe that are beyond the observable horizon, hidden behind the cosmic event horizon of black holes or the limitations of current technology. We will never be able to observe the entirety of the universe, and there will always be regions of space that remain beyond our detection. Yet, it is precisely this infinite expanse of the unknown that fuels our curiosity and drives us to keep exploring. With every new discovery, we are reminded that the universe is not a final destination, but a journey that will continue to unfold in ways we cannot yet imagine. The more we discover about the observable universe, the more we realize that the answers we seek often lead to new, deeper questions. Each observation, each revelation, opens the door to a broader understanding of the cosmos, and our place within it. As we continue to explore the universe, we are reminded that the search for knowledge is not a finite process but an ongoing adventure, one that will continue to inspire generations of explorers, scientists, and dreamers for centuries to come. The observable universe is not just a scientific concept, it is a reflection of our deepest desires to understand the cosmos and our place within it, a reminder that the mysteries of existence are infinite, and that the pursuit of knowledge is the ultimate journey. Cosmic inflation, first proposed by Alan Guth in the early 1980s, describes a rapid exponential expansion of the universe that occurred fractions of a second after the Big Bang. This sudden growth stretched the fabric of space-time, smoothing out irregularities and laying the groundwork for the large-scale structures we observe today. However, inflation theory also suggests that this process could continue in other regions of space, creating isolated pocket universes. These pockets, or bubble universes, could form distinct realms, each governed by its own set of physical laws and constants, making them radically different from our observable cosmos. The idea of bubble universes ties into the larger framework of the multiverse, where these isolated regions coexist within a vast cosmic expanse. While our universe appears uniform and predictable, other universes could operate under entirely different principles. For instance, one universe might have a stronger gravitational constant, resulting in faster star formation, while another might lack the conditions necessary for the formation of matter as we know it. The possibilities are endless, and the implications are profound, challenging our understanding of what it means to exist. Adding to this complexity is string theory, a groundbreaking framework in theoretical physics that introduces the concept of higher dimensions. Traditional physics describes the universe in 3 spatial dimensions and 1 dimension of time. However, string theory posits the existence of additional spatial dimensions, up to 10 or 11 dimensions in some models. These dimensions are compactified, meaning they are curled up and imperceptible to our senses, but they play a crucial role in the behavior of fundamental particles and forces. In string theory, and curiosity, driving scientists to push the boundaries of knowledge. Projects like the James Webb Space Telescope and future particle accelerators aim to explore the origins of the universe, and the fundamental nature of reality. By studying the behavior of particles, the distribution of galaxies, and the faint echoes of the Big Bang, researchers hope to uncover evidence that could confirm or refute the existence of a multiverse. The implications of a multiverse are staggering. If other universes exist, they might contain forms of matter and energy that defy our understanding. They could harbor exotic life forms, governed by entirely different physical laws, or even lack life altogether, existing as sterile realms of pure energy or dark matter. The diversity of possibilities highlights the limitations of our current knowledge and the vast potential for discovery. The multiverse theory and the concept of higher dimensions have emerged as some of the most exciting and controversial ideas in modern cosmology, stretching the boundaries of what we know and challenging us to think in entirely new ways. These theories push us to imagine the universe not as a singular, isolated entity but as part of a much larger, more complex reality, full of infinite possibilities. They invite us to explore beyond the confines of the observable universe, offering a glimpse into realms that are entirely different from our own, yet intricately woven into the very fabric of reality. As we venture into these uncharted territories of thought, we are not just expanding the frontiers of science, we are grappling with profound questions that have intrigued and captivated humanity for millennia. The idea of the multiverse suggests that our universe is not the only one, but rather part of a vast collection of parallel or alternate universes. Each of these universes could have different physical laws, constants, and properties, leading to realities that may be radically different from our own. This concept is rooted in several areas of theoretical physics, including string theory and quantum mechanics, where the mathematical models suggest that the universe we perceive is just one among many possible realities. Some versions of the multiverse theory propose that these universes are completely separate, while others suggest that they may interact in subtle ways or even collide with one another, giving rise to new phenomena. The most famous version of the multiverse theory comes from cosmology and the concept of inflation. According to the theory of inflation, the universe underwent a rapid period of expansion just moments after the Big Bang, growing exponentially in size over a fraction of a second. This expansion is thought to have created regions of space where different universes could form, each with its own set of physical laws. In this model, the multiverse is a vast, constantly expanding collection of these pocket universes, each existing within its own bubble, with different outcomes determined by slight variations in initial conditions. While the multiverse theory remains highly speculative and controversial, it presents some intriguing possibilities. If the multiverse exists, it could help explain some of the mysteries of our own universe. For example, the apparent fine-tuning of physical constants, such as the strength of gravity or the mass of elementary particles, could be a result of the fact that our universe is one of many, with only those universes that happen to have the right conditions for life surviving long enough to be observed. The multiverse could offer a natural explanation for why our universe appears to be so perfectly suited for the emergence of life. The fine-tuning of the constants, in this view, may not be the result of some cosmic design but simply a consequence of a vast, randomly generated landscape of universes, with ours being one of the fortunate few to possess the right conditions for life to thrive. Another fascinating aspect of the multiverse theory is its potential to answer some of the deepest questions in philosophy and theology. For centuries, humanity has pondered the nature of existence and the possibility of multiple realities. The multiverse theory, by suggesting that there could be an infinite number of parallel universes, provides a framework for thinking about questions such as whether there could be other versions of ourselves, living in different worlds with different circumstances, or whether other forms of life might exist in entirely separate universes. These questions, while speculative, open up new avenues of thought that challenge our understanding of reality and our place in the cosmos. If the multiverse exists, it could also have profound implications for our understanding of free will, determinism, and the nature of the self, as different versions of reality may give rise to different choices, paths, and outcomes. While the multiverse theory has captured the imagination of physicists, philosophers, and even science fiction writers, it is far from the only idea that challenges our conventional understanding of reality. The concept of higher dimensions is another bold leap into the unknown, proposing that our universe may contain more than the familiar three dimensions of space and one of time. According to some theories, the fabric of the universe could be made up of many more dimensions, which we cannot perceive directly because they are compactified, curled up, or hidden at scales far smaller than those accessible to our current instruments. These extra dimensions are a central feature of string theory, which suggests that the fundamental particles that make up matter are not point-like objects but rather tiny vibrating strings, and that the vibrations of these strings occur in multiple dimensions. The idea of higher dimensions was first proposed in the 19th century by mathematicians and physicists as a way to explain certain aspects of geometry and gravity. However, it gained more prominence in the late 20th century with the development of string theory and M-theory, which suggest that the universe is not just made up of three spatial dimensions but may involve as many as 11 or more dimensions. These extra dimensions could be hidden from our perception, either because they are compactified at extremely small scales, as in the case of string theory, or because they exist at higher energy levels that are beyond our current detection methods. If these extra dimensions exist, they could help explain some of the most perplexing questions in physics, including the nature of gravity and the relationship between the fundamental forces of nature. The search for knowledge has been a fundamental driving force behind human progress throughout history. From the earliest days of civilization, we have sought to understand further. Our understanding of space is grounded in the familiar three dimensions of length, width, and height. However, theories such as string theory and M-theory suggest that there could be many more dimensions beyond the ones we can perceive. These extra dimensions, though hidden from our senses, could play a crucial role in the workings of the universe. The idea that there are more dimensions to explore opens up new possibilities for understanding the fundamental forces of nature and the connections between different particles and forces in the universe. It suggests that reality itself may be far more complex than we ever imagined. These theories of the multiverse and higher dimensions represent the cutting edge of scientific thought, yet they also remind us of the limitations of our current knowledge. They push us to think in new ways, to question the assumptions we have held for centuries, and to explore realms that were once thought to be beyond our reach. In doing so, they inspire us to continue exploring the unknown, to keep asking questions, and to never stop dreaming about the mysteries that lie just beyond our grasp. As humanity ventures deeper into the realms of theoretical physics and cosmology, we are reminded that the pursuit of knowledge is an ongoing journey, one that calls us to venture further into the unknown, ever seeking the answers that lie hidden in the vast expanse of space and time. Each new theory, each new discovery, brings us closer to understanding the nature of existence itself. The search for knowledge, driven by our curiosity and imagination, will continue to propel us forward, as we strive to unlock the secrets of the universe and uncover the infinite possibilities that lie beyond. Black holes, some of the most enigmatic and powerful entities in the universe, play a pivotal role in shaping cosmic evolution. From their formation to their profound influence on surrounding matter, black holes are central to our understanding of the dynamics of galaxies and the behavior of spacetime itself. These objects, which include both stellar black holes and supermassive black holes, exert their influence even at the outer reaches of the universe, where the fabric of space begins to stretch and galaxies thin out. Stellar black holes are born from the collapse of massive stars. When a star exhausts its nuclear fuel, its core can no longer resist the pull of gravity, leading to an implosion that forms a dense singularity. These black holes, typically a few times the mass of the Sun, are scattered throughout galaxies and can significantly impact their local environments. Supermassive black holes, on the other hand, are colossal entities found at the centers of most galaxies, including our own Milky Way. These giants, with masses ranging from millions to billions of times that of the Sun, are thought to have formed in the early universe, possibly through the merging of smaller black holes or the accretion of vast amounts of matter over time. The role of supermassive black holes in cosmic evolution is profound. Their immense gravitational pull influences the structure and behavior of galaxies. As gas and dust spiral into these black holes, they form accretion disks that heat up and emit intense radiation. This process, often seen in active galactic nuclei, AGN, can generate powerful jets of energy that stretch across millions of light years. These jets not only illuminate the cosmos but also regulate star formation within galaxies by heating and dispersing surrounding gas. This phenomenon, known as feedback, ensures that galaxies do not grow uncontrollably, maintaining a balance in the cosmic ecosystem. At the universe's edge, black holes offer a unique lens through which to study the nature of gravity, space, and time. Their extreme environments push the limits of physics, providing insights into phenomena such as gravitational waves, which are ripples in spacetime caused by massive objects accelerating. The detection of these waves, first achieved by LIGO in 2015, marked a breakthrough in our ability to observe cosmic events. Gravitational waves from merging black holes offer a new way to probe the universe, allowing scientists to study regions and processes that are otherwise invisible. Black holes also highlight the interconnectedness of various cosmic entities. For instance, interactions between black holes and their host galaxies reveal the symbiotic relationship that shapes the evolution of both. Observations of distant quasars, which are powered by supermassive black holes, provide a glimpse into the early universe, showing how galaxies formed and evolved billions of years ago. Quasars, among the brightest objects in the universe, emit light that travels vast distances, carrying with it information about the conditions of the cosmos when it was young. The study of black holes at cosmic extremities extends our understanding of fundamental physics. These objects challenge our knowledge of relativity and quantum mechanics, as their singularities represent points where the known laws of physics break down. Efforts to reconcile these theories, such as through quantum gravity, are driven by observations of black holes and their behavior. The Event Horizon Telescope's capture of the first image of a black hole in 2019, located in the galaxy M87, was a monumental achievement, offering direct evidence of these elusive entities and opening new avenues of research. Black holes are not merely destructive forces, they are also creators in their own right. The energy and matter they eject during interactions with their surroundings contribute to the enrichment of the interstellar medium, facilitating the formation of new stars and planets. By studying black holes, scientists uncover the processes that govern the universe's evolution, from the smallest scales of particle interactions to the grandest structures of galaxy clusters. The presence of black holes at the edges of the universe underscores their universal significance. Even in regions where matter is sparse, black holes can influence the motion and fate of celestial bodies. Their gravitational pull shapes the paths of stars and gas, creating patterns that help scientists map the large-scale structure of the cosmos. Developments in modern cosmology has been the discovery of the intergalactic effects of supermassive black holes. It was once thought that black holes were isolated objects, confined to the centers of galaxies. However, observations made by powerful telescopes such as the Hubble Space Telescope and the Event Horizon Telescope have shown that the influence of black holes extends far beyond their immediate surroundings. In fact, the energy and radiation produced by black holes can have a far-reaching impact on the intergalactic medium, the vast stretches of space between galaxies that are filled with diffuse gas and dark matter. This energy output can help to heat and ionize the intergalactic medium, affecting the formation of structures in the universe and influencing the overall dynamics of cosmic expansion. The extreme conditions near a black hole also raise profound questions about the nature of information and its role in the universe. According to classical physics, Information that falls into a black hole is lost forever, as the matter is crushed into a singularity at the center of the black hole. However, this idea is in direct conflict with quantum mechanics, which asserts that information cannot be destroyed. This apparent contradiction is known as the black hole information paradox, and it has led to one of the most significant challenges in theoretical physics. While various hypotheses have been proposed to resolve this paradox, including the idea that information is stored on the surface of the black hole, a concept known as the holographic principle, the ultimate resolution remains elusive. Despite the many unanswered questions about black holes, one of the most groundbreaking discoveries in recent years has been the direct observation of a black hole's event horizon. In April 2019, the Event Horizon Telescope (EHT) collaboration revealed the first ever image of a black hole's event horizon, located in the center of the galaxy M87. This historic image provided concrete evidence of the existence of supermassive black holes and confirmed many of the predictions made by general relativity. The image, which showed a dark, circular shadow surrounded by a glowing ring of gas and light, offered a glimpse into one of the most enigmatic objects in the universe. It was a breakthrough that marked a new era in our understanding of black holes and their role in the cosmos. Black holes are far more than just cosmic objects that consume matter. They are powerful forces of creation and destruction, shaping the evolution of galaxies and the universe itself. Their study continues to deepen our understanding of the cosmos, offering insights into the fundamental nature of reality. As we continue to observe and explore these enigmatic objects, we are reminded of the vastness of the universe and the infinite mysteries that remain to be uncovered. Black holes are not only the destroyers of worlds but also the creators of new realms of understanding, inspiring generations of scientists, philosophers, and dreamers to unravel the deepest mysteries of existence. The cosmic microwave background, CMB, a faint radiation glow that permeates the universe, offers an unparalleled glimpse into its infancy and early structure. This radiation, a direct remnant of the Big Bang, is a snapshot of the cosmos, when it was only 380,000 years old, providing critical clues about the conditions that shaped the universe as we know it. First detected by Arno Penzias and Robert Wilson in 1965, the CMB has become a cornerstone of modern cosmology, serving as a window into the universe's early moments and the processes that set its evolution in motion. The CMB's importance lies in the wealth of information embedded within its fluctuations, tiny variations in temperature and density that reflect the distribution of matter in the early universe. By analyzing these fluctuations, scientists can trace the seeds of galaxy formation, identifying regions where matter coalesced under the influence of gravity to form stars and galaxies. These patterns, mapped with exquisite precision by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have revealed the intricate blueprint of the cosmos, confirming the predictions of the Big Bang theory and refining our understanding of the universe's composition and age. One of the most profound revelations from CMB studies is the accelerating expansion of the universe, a discovery that has reshaped our understanding of cosmic dynamics. This acceleration is attributed to a mysterious force known as dark energy, which constitutes approximately 73% of the universe's total energy content. Unlike gravity, which pulls objects together, dark energy exerts a repulsive force, driving galaxies apart at an ever-increasing rate. The discovery of dark energy in the late 1990s, through observations of distant supernovae, marked a paradigm shift in cosmology, highlighting the dynamic nature of the universe and challenging existing theories of physics. Complementing the story of the CMB is the equally enigmatic concept of dark matter, an invisible substance that makes up about 27% of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it undetectable through traditional observational methods. Its presence is inferred from its gravitational effects on visible matter, such as the rotation curves of galaxies and the behavior of galaxy clusters. Dark matter acts as the scaffolding of the cosmos, providing the gravitational framework within which galaxies and larger structures form and evolve. The interplay between dark matter and the CMB is crucial to understanding the universe's evolution. As the universe expanded and cooled, dark matter began to clump together, creating the gravitational wells that attracted ordinary matter. These wells correspond to the fluctuations observed in the CMB, marking the sites where galaxies and stars would eventually form. Without dark matter, the universe's structure as we know it would not exist, as ordinary matter alone lacks the gravitational strength to form the intricate web of galaxies that fills the cosmos. The study of dark matter has driven some of the most ambitious experiments. And dark energy, they are uncovering a universe that is both more intricate and more mysterious than ever imagined. Each discovery builds on the foundation laid by earlier observations, from the first detection of the CMB to the identification of dark energy. These breakthroughs not only expand our knowledge of the cosmos, but also inspire new questions about its origins, structure, and destiny. The study of the cosmic microwave background, CMB, and dark matter is a powerful testament to the innate human curiosity and the relentless pursuit of knowledge. These two enigmatic aspects of the universe have opened windows into the deepest mysteries of the cosmos, offering invaluable insights into the origins, structure, and evolution of the universe. Through the study of the faint whispers of the Big Bang captured in the CMB, and the invisible but influential presence of dark matter, scientists are unraveling the intricate and often elusive story of the cosmos, stretching across billions of years and revealing a vast narrative that encompasses the entire fabric of space and time. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was a monumental moment in cosmology, confirming the Big Bang theory and providing strong evidence that the universe had a definitive beginning. Since then, the study of the CMB has become a cornerstone of modern cosmology, with missions like the Planck satellite and WMAP mapping the CMB with incredible precision. These observations have led to the development of the Lambda CDM model, which is the standard model of cosmology and has provided an accurate description of the universe's evolution, from its inception to its present state. Together, the study of the CMB and dark matter reveals a universe that is far more complex and mysterious than we can fully comprehend. The CMB allows us to look back to the earliest moments of the universe, while dark matter points to unseen forces that continue to shape its evolution. As scientists continue to probe these mysteries, they are not only piecing together the history of the cosmos but are also expanding the boundaries of knowledge, laying the groundwork for future discoveries that could redefine our understanding of the universe. The study of the CMB and dark matter exemplifies the power of human curiosity. Through these investigations, scientists are uncovering a narrative of the cosmos that stretches across unimaginable spans of time, offering us a glimpse into the universe's past, present, and future. The journey to understand these profound phenomena continues to inspire and challenge our imagination, as we strive to understand the universe we call home. This ongoing pursuit of knowledge serves as a reminder of the boundless potential of human exploration, and our unyielding desire to comprehend the cosmos. Observing the universe's farthest reaches offers a unique glimpse into the processes that shaped its earliest structures. Distant galaxies, lying billions of light-years away, are cosmic time capsules, revealing the universe as it was during its formative years. These galaxies formed under the extreme conditions of the early universe, a time characterized by intense radiation, high temperatures, and the rapid cooling of primordial gas. The study of these distant galaxies provides critical insights into the mechanisms of galaxy formation and evolution, piecing together the story of cosmic history. In the early universe, the density of matter was significantly higher than it is today, creating an environment conducive to rapid star formation. Observations have shown that distant galaxies often exhibit star formation rates much higher than those in the local universe. These starburst galaxies, forming hundreds or even thousands of stars per year, contrast sharply with the relatively sedate pace of star formation in modern galaxies like the Milky Way, which forms only a few stars annually. This frenetic activity in the early universe suggests that the conditions for star formation were markedly different, shaped by the availability of gas, intense gravitational interactions, and the influence of dark matter. Key to understanding these high star formation rates is the role of cosmic events, such as radiation from bright stars and the activity of supermassive black holes. Radiation from newly formed stars creates feedback effects, heating the surrounding gas and sometimes suppressing further star formation. Simultaneously, the gravitational pull of supermassive black holes at the centers of these galaxies influences the distribution and motion of matter. As gas spirals into these black holes, it forms accretion disks that emit intense energy, shaping the broader galactic environment. This interplay between star formation and black hole activity creates a dynamic ecosystem within early galaxies, driving their growth and evolution. The extreme conditions of the early universe also gave rise to frequent galactic mergers and interactions. In this era, galaxies were closer together, leading to more collisions and gravitational encounters. These interactions played a pivotal role in shaping galaxy morphology, triggering bursts of star formation, and redistributing gas and stars. Observations of these processes, made possible by powerful telescopes like the James Webb Space Telescope, JWST, and the Hubble Space Telescope, have revealed intricate details about how galaxies interact and evolve over time. Another crucial aspect of studying galaxies at the universe's edge is the role of dark matter in their formation. Dark matter, an invisible substance that does not emit or absorb light, provides the gravitational scaffolding around which galaxies form. In the early universe, dark matter clumps created gravitational wells that attracted ordinary matter, initiating the processes of star and galaxy formation. These dark matter halos continue to influence the structure and dynamics of galaxies, shaping their rotation curves and interactions with other cosmic entities. Studying these distant galaxies aids in constructing a timeline of cosmic history, revealing the sequence of events that led to the universe's current state. By examining galaxies at different distances, and thus at different we not only seek to understand the forces that have shaped galaxies over cosmic time but also uncover the underlying principles that govern the structure and evolution of the universe itself. The discovery of galaxies at the edge of the observable universe is not just an intellectual exercise, it is a journey of exploration that challenges the limits of human knowledge and inspires a deep sense of wonder about the vast, interconnected cosmos. Galaxies, the massive systems of stars, gas, dust, and dark matter bound together by gravity, are the fundamental building blocks of the universe. They come in a variety of shapes and sizes, from the well-ordered spirals like the Milky Way to the irregular forms seen in distant galaxies. When we observe galaxies at the edge of the universe, we are not just looking at the light from these distant objects but also peering back in time. Due to the finite speed of light, the light that we observe from a galaxy billions of light-years away, has traveled across space for billions of years. This means that when we look at these distant galaxies, we are observing them as they were in the past, sometimes when the universe itself was only a few 100 million years old. In a sense, every distant galaxy is a snapshot of a time long gone, a cosmic relic from an era when the universe was young and still forming. The discovery and study of these galaxies at the universe's edge have profound implications for our understanding of the early universe. One of the most important aspects of this research is its role in shedding light on the formation and evolution of cosmic structures. Galaxies are not static entities, they are dynamic systems that evolve over time, influenced by a variety of factors including gravitational interactions, supernova explosions, and black hole activity. Observing galaxies at different stages of evolution allows scientists to piece together the complex history of galaxy formation and the processes that have shaped their development. This research can also provide clues about the formation of the universe itself, shedding light on the conditions that existed in the aftermath of the Big Bang and how those conditions gave rise to the universe we see today. One of the most exciting aspects of studying galaxies at the edge of the universe is the opportunity it provides to examine early cosmic epochs. By studying galaxies that formed only a few 100 million years after the Big Bang, astronomers can begin to understand how the first stars and galaxies were born. During this period, the universe was transitioning from the hot, dense state of the early universe into the more structured cosmos that we observe today. This era, known as the cosmic dawn, is a critical phase in the evolution of the universe, and the galaxies formed during this time hold key information about the processes that drove the birth of stars and galaxies. Observing these early galaxies can provide insights into the ionization process, a phase in the universe's history when the first stars and galaxies ionized the hydrogen gas that permeated the early universe, allowing light to travel freely through space for the first time. At the universe's edge, we also encounter some of the most extreme and energetic phenomena in the cosmos. Many of these galaxies harbor active galactic nuclei, AGN, powered by supermassive black holes at their centers. These black holes accrete vast amounts of matter, generating intense radiation and powerful jets of particles that can stretch across enormous distances. The study of AGNs provides valuable information about the growth of supermassive black holes and their influence on the galaxies around them. These extreme environments challenge our understanding of the fundamental forces of nature, including gravity, electromagnetism, and nuclear forces. The energetic processes observed in these galaxies can reveal new insights into the nature of spacetime, the behavior of matter under extreme conditions, and the evolution of cosmic structures. The study of galaxies at the universe's edge is also crucial for understanding the cosmic web, the large-scale structure of the universe. Galaxies are not distributed randomly throughout space, instead, they form clusters, superclusters, and vast filaments that stretch across the universe. These structures are thought to be shaped by the distribution of dark matter and the gravitational forces that result from it. By mapping the locations and properties of galaxies at the universe's edge, astronomers can learn more about the distribution of dark matter and how it has shaped the large-scale structure of the universe. This research provides important clues about the nature of dark matter and its role in the evolution of the cosmos. Perhaps one of the most profound implications of studying galaxies at the edge of the universe is the way in which it highlights the interconnectedness of all things. As we observe the light from these distant galaxies, we are not simply looking at isolated objects in space but are instead gazing at fragments of a much larger, interconnected cosmic tapestry. The light from these galaxies has traveled across vast expanses of space, passing through the fabric of the universe and interacting with the elements of spacetime along the way. Every observation we make is a part of a larger story, a story that stretches across the vastness of time and space, linking the present to the distant past and offering us a glimpse of the future. The study of these distant galaxies is a reminder of the humbling vastness of the universe. Even though these galaxies are located billions of light-years away, the light we observe from them is a part of us. It is a part of the universe that we inhabit, a universe that is far more complex and mysterious than we can fully comprehend. As we peer into the depths of space, we are confronted with the enormity of the cosmos and reminded of our place within it. Our observations, discoveries, and explorations are just the beginning of a journey that stretches into infinity, as we seek to understand not only the farthest reaches of space but also the fundamental questions that define our existence. The study of galaxies at the universe's edge is not only a scientific endeavor but a profound journey of discovery that ignites a sense of awe and wonder. These distant galaxies, forged in the crucible of the early universe, reveal the fascinating and largely unexplored aspect of the universe. One of the most intriguing aspects of rogue planets is their potential to harbor internal heat sources. While they lack the warmth and light of a nearby star, rogue planets may generate heat through processes such as radioactive decay or residual energy from their formation. In some cases, thick atmospheres or insulating layers of ice could trap this heat, creating conditions that might support liquid water and, potentially, life. This possibility expands the scope of astrobiology, suggesting that habitable environments might exist even in the cold, dark voids of interstellar space. On Earth, extremophiles, organisms that thrive in extreme conditions, provide a compelling model for understanding how life might adapt to such environments. These resilient life forms have been discovered in some of the harshest habitats on our planet, from boiling hydrothermal vents at the ocean floor to the frigid deserts of Antarctica. Their ability to survive and even flourish under extreme pressure, temperature, and radiation levels inspires hypotheses about the potential for similar organisms to exist on rogue planets. If life can adapt to the extremes of Earth, it raises the tantalizing possibility that it could also arise in the uncharted environments of these wandering worlds. Detecting rogue planets presents a significant observational challenge due to their lack of stellar illumination. However, advancements in astronomical techniques have begun to uncover these elusive objects. Gravitational microlensing, a method that detects the bending of light from a distant star as a massive object passes in front of it, has proven particularly effective in identifying rogue planets. This technique, combined with data from missions like the Kepler Space Telescope and future observatories such as the Nancy Grace Roman Space Telescope, is expanding our ability to detect and study these solitary worlds. The discovery of rogue planets has profound implications for our understanding of planetary systems and the diversity of cosmic environments. These wandering worlds challenge traditional models of planet formation, suggesting that ejection events might be a common outcome in the early evolution of planetary systems. Moreover, the sheer number of rogue planets, potentially outnumbering stars in the galaxy, highlights their significance as a major component of the universe's planetary population. Rogue planets also offer a unique perspective on the resilience of life and the adaptability of planetary systems. If these planets can sustain life or even prebiotic conditions in the absence of a star, it would redefine the boundaries of habitability and our understanding of life's potential to thrive in the universe. Such discoveries would have profound implications for astrobiology, expanding the range of environments considered conducive to life, and inspiring new avenues of research. Rogue planets, also known as interstellar planets or nomad planets, are thought to originate in star-forming regions, where gravitational disturbances, such as interactions with nearby stars or giant molecular clouds, can cause planets to be ejected from their original systems. While these planets do not orbit a star, they may still possess the internal heat generated from their initial formation or from radioactive decay, making them capable of supporting complex environments despite their isolation in deep space. In recent years, technological advancements in detection methods, such as gravitational microlensing and infrared imaging, have allowed scientists to identify more of these rogue worlds, expanding our understanding of how planetary systems can form and evolve in ways previously thought impossible. One of the most intriguing aspects of rogue planets is their extreme and unique environments. Without a star to provide light and heat, these planets exist in perpetual darkness and cold, far from the warmth of a solar system's central star. However, this does not mean that rogue planets are devoid of potential for habitability. Some may harbor subsurface oceans kept warm by geothermal heat or tidal forces from large moons or nearby objects, creating the conditions for life as we understand it, or perhaps forms of life yet to be imagined. The discovery of such environments invites questions about the resilience of life, pushing the boundaries of our definition of what constitutes a habitable planet, and challenging the assumption that life can only exist in the Goldilocks zone of a star's habitable zone. The search for rogue planets also enriches our understanding of the universe's vast and varied environments. While they might appear to be lifeless and cold, they represent a broader definition of what a planet can be, extending our imagination and expanding the scope of possibilities in planetary science. The study of these rogue worlds reveals the resilience of planetary systems and offers a unique perspective on how planets and stars interact within the cosmic landscape. Furthermore, rogue planets exemplify the dynamic nature of the universe. They are not tied to the gravitational constraints of a star, and their unpredictable paths through space illustrate the forces of nature at play in the vast reaches of the cosmos. These planets drift through the galaxy, free from the gravitational confines of a system, yet they are still shaped by the powerful forces that govern the movement of matter throughout space. The study of these solitary travelers provides valuable insights into the forces that influence planetary systems and offers a reminder of the cosmos' ever-changing nature. Through the study of rogue planets, we gain not only a deeper understanding of planetary systems but also a renewed sense of wonder about the universe itself. These planets embody the limitless diversity of the cosmos, challenging our assumptions and inspiring new questions about the nature of the universe and the potential for life beyond the stars. They remind us that the universe is full of surprises, and that even in the coldest, darkest corners of space, there may be hidden worlds teeming with possibilities, waiting to be discovered. Rogue planets stand as a testament to the complexity and unpredictability of the universe. These lone wanderers, unbound by the gravity of a star, illustrate the dynamic and ever-changing nature of cosmic environments. By studying these planets and extreme cosmic environments, we gain invaluable insights into planetary formation, the resilience of life, and the potential for diverse worlds to exist in the vastness of space. The study of rogue planets challenges our understanding, pushing the limits of exploration and inspiring awe in the infinite possibilities that lie beyond our current knowledge of the universe. CMB. These questions are at the forefront of modern cosmology, driving efforts to explore the fundamental nature of reality and the limits of our observational capabilities. The concept of a multiverse is not confined to bubble cosmology. It also emerges in other areas of theoretical physics, such as string theory and the many worlds interpretation of quantum mechanics. String theory, which posits the existence of additional spatial dimensions, suggests that our universe might be a three-dimensional brane floating within a higher dimensional space. This framework allows for the possibility of multiple branes, each corresponding to a distinct universe with its own unique properties. Meanwhile, the many worlds interpretation of quantum mechanics proposes that every quantum event spawns a new universe, creating an ever-branching tree of parallel realities. The philosophical implications of parallel universes are as profound as their scientific foundations. If multiple universes exist, what does this mean for the concept of individuality and identity? Could there be alternate versions of ourselves living entirely different lives in other universes? These questions challenge our understanding of reality and the nature of existence, inviting us to consider the interconnectedness of all things and the possibility that our universe is just one piece of a vast, incomprehensible whole. While the existence of parallel universes remains speculative, the theories that support them are grounded in some of the most well-established principles of physics. Cosmic inflation, quantum mechanics, and string theory provide robust frameworks for exploring the multiverse, offering testable predictions and guiding the search for evidence. Each step forward in this field deepens our understanding of the universe and its place within the broader cosmic context, inspiring new questions and possibilities. As we venture into the realms of theoretical physics, the ideas of parallel universes and bubble cosmology open up an entirely new dimension of thought. These concepts push the boundaries of our understanding, inviting us to explore the very nature of reality itself and challenge our perception of what is possible within the universe. The notion that our universe may be one among many, or that the fabric of reality might stretch across multiple dimensions, offers an expansive canvas for the imagination and represents the frontier of modern cosmology. While these theories remain speculative and not yet grounded in empirical evidence, they reflect the boundless potential of human curiosity and the infinite complexity of the cosmos. The idea of parallel universes, also known as the multiverse theory, suggests that there may be an infinite number of universes beyond our own, each with its own set of physical laws and properties. These universes may coexist in the same space-time framework but remain invisible to us due to their distinct characteristics. In some versions of the multiverse theory, these universes could be fundamentally different from our own, with alternative laws of physics, varying constants, and even different forms of matter and energy. In others, they might closely resemble our universe, with slight differences in their histories or configurations of matter. The concept of parallel universes challenges our understanding of what is real, offering a view of the cosmos that is far more complex and interconnected than our everyday experiences suggest. The idea of parallel universes is rooted in several areas of theoretical physics. One prominent model comes from quantum mechanics, where the many worlds interpretation posits that every possible outcome of a quantum event actually occurs, but in different, parallel realities. In this interpretation, when a quantum system undergoes measurement, the universe splits into multiple versions, with each version corresponding to a different outcome. For example, if a particle has a 50% chance of being in one state, and a 50% chance of being in another, the universe would branch into two, each with a different version of the particle's state. This idea, while intriguing, remains highly speculative, as it is difficult to test or observe the existence of these parallel universes. Bubble cosmology, or the inflationary multiverse model, takes inspiration from the theory of cosmic inflation, which suggests that the early universe underwent a rapid expansion immediately following the Big Bang. In some versions of inflationary theory, this process continues indefinitely, creating pocket or bubble universes within a larger, eternal inflationary framework. Each bubble would represent a separate universe with its own distinct properties and laws of physics. While the space between these bubbles would be separated by regions that are not accessible to us, the idea that an infinite number of universes could exist, each with different characteristics, suggests an unimaginably vast cosmos that extends far beyond our current observational limits. The study of parallel universes and bubble cosmology raises profound questions about the nature of existence itself. If these theories are correct, they imply that our universe is just one of many, each with its own unique history and potential. This challenges the notion that our universe is the only reality, and instead suggests that our existence might be part of a much larger and interconnected multiverse. If parallel universes are real, they could harbor alternate versions of ourselves, where different decisions or events have led to entirely different outcomes. The idea that every possible reality could exist somewhere in the multiverse compels us to rethink the nature of free will, fate, and the choices we make. These theories also ignite a deeper appreciation for the interconnectedness of existence. If parallel universes exist, they are not isolated from one another but are intricately woven together within the framework of a greater reality. The forces and laws that govern our universe may extend beyond our own realm, influencing and interacting with other universes in ways that are currently beyond our comprehension. In this context, the study of parallel universes and bubble cosmology is not just an intellectual pursuit but a philosophical exploration of the very nature of reality itself. Moreover, these ideas challenge us to embrace the unknown. The pursuit of knowledge has always driven humanity to explore the uncharted and the unexplored, from the depths of the ocean to the farthest reaches of space. The concept of parallel universes invites us to expand our imaginations and venture beyond the boundaries of the observable, acknowledging that there may be countless other realms of existence that we cannot yet detect or comprehend. This pursuit is not only about uncovering new facts and theories, it is about recognizing the inherent mystery of the universe and the vast unknown that awaits discovery. While the study of parallel universes and bubble cosmology is still in its infancy and remains speculative, the very existence of these ideas serves as a testament to human ingenuity and curiosity. These theories push the limits of scientific inquiry, inspiring new generations of physicists, cosmologists, and philosophers to explore the nature of the cosmos, and our place within it. They invite us to think about the universe in ways that challenge our assumptions, broaden our perspectives, and deepen our understanding of the profound mysteries that lie at the heart of reality. The contemplation of parallel universes and bubble cosmology encourages us to think beyond the observable, and embrace the infinite possibilities of the cosmos. These theories offer a glimpse into the boundless potential of human imagination and the deep, interconnected nature of existence. By expanding our understanding of the universe and questioning the very nature of reality, we gain not only new insights into the cosmos but also a renewed sense of wonder and curiosity that drives us to explore the profound mysteries of the universe. The study of parallel universes invites us to consider the possibility that our reality is just one among many, and in doing so, it opens the door to a broader understanding of the universe and our place within it. The universe is a vast and ever-changing expanse, a place where phenomena defy the imagination. Among the most fascinating occurrences within this cosmic canvas are the rare and powerful events that give us glimpses into the origins of the universe, the mechanics of celestial bodies, and the intricate processes that shape the very fabric of space and time. These events, which include gamma-ray bursts, quasar emissions, the mysteries of cosmic strings, and the explosive power of supernovae, are pivotal in understanding the history and evolution of the universe. By examining these cosmic events and exotic phenomena, scientists unlock the secrets of our cosmic origins, as well as the forces that continue to influence the expansion and structure of the universe. One of the most spectacular and mysterious phenomena observed in deep space are gamma-ray bursts, GRBs. These brief but incredibly powerful explosions of gamma rays represent some of the most energetic events known to humankind. The bursts are thought to be the result of cataclysmic events such as the collapse of massive stars into black holes or the collision of neutron stars. First observed in 1967 by accident when the U.S. military satellites detected bursts of gamma radiation, scientists initially struggled to understand their origin. It wasn't until the 1990s, when the burst sources were pinpointed to distant galaxies, that GRBs were recognized as a potential window into the universe's most extreme and earliest epochs. Gamma-ray bursts are crucial in the study of the early universe. The intense energy released by these events can be detected across vast cosmic distances, providing valuable insights into the conditions that existed in the universe's infancy. Because GRBs can be observed from billions of light-years away, they act as beacons, allowing astronomers to peer into the distant past, back to a time when the universe was only a fraction of its current age. The energy emitted by a gamma-ray burst in just a few seconds can exceed the amount of energy the Sun will emit over its entire 10 billion-year lifetime. This makes them not only powerful phenomena but also useful tools for probing the distant past. Another remarkable aspect of the universe's edge lies in the study of quasars. Quasars are the brightest and most energetic objects in the universe, often outshining entire galaxies. They are powered by supermassive black holes, which reside at the centers of distant galaxies. When matter is pulled into these black holes, the immense gravitational forces cause the material to accelerate and heat up, emitting vast amounts of electromagnetic radiation. This process leads to the creation of an active galactic nucleus, AGN, which is the region around the black hole where these emissions occur. Quasars were first identified in the 1960s as objects with strange spectral lines, and their extreme luminosity has made them a subject of intense study. The discovery of quasars was groundbreaking because it provided strong evidence for the existence of supermassive black holes, objects so dense that not even light can escape their gravitational pull. These discoveries have significantly altered our understanding of the structure and evolution of galaxies. Quasars are thought to have been much more common in the early universe, with many of them being formed during the first billion years after the Big Bang. By studying the emissions from quasars, astronomers gain a clearer picture of how galaxies, supermassive black holes, and the larger cosmic structure evolved over time. Quasars also provide insight into the large-scale structure of the universe. As light from distant quasars travels through space, it passes through various cosmic structures, such as gas clouds and dark matter. The interactions between quasar light and these structures reveal much about the distribution of matter throughout the universe. Quasars, in essence, serve as cosmic lighthouses, illuminating the vast and largely invisible regions of space between us and the farthest reaches of the observable universe. This enables scientists to map the evolution of the universe, from its earliest stages to its current state. Beyond gamma-ray bursts and quasars, another enigmatic phenomenon that has captured the attention of cosmologists is cosmic strings. These hypothetical structures are thought to be extremely thin, one-dimensional defects in spacetime that could have formed in the early universe. They are believed to have emerged during the phase transitions in the early universe, moments when different forces in nature separated from each other as the universe cooled. Cosmic strings would be extraordinarily dense, and their gravitational effects could potentially be observed as they warp spacetime around them. Although no direct evidence for cosmic strings has yet been found, their theoretical implications are profound. If they exist, they could provide crucial clues about the nature of the universe's infancy, as well as the fundamental forces that govern it. The discovery of cosmic strings would force scientists to reconsider current models of cosmology and particle physics, and it would open up new avenues of exploration regarding the very fabric of spacetime. Some theorists suggest that cosmic strings could even be linked to the mysterious phenomenon of dark matter, a substance that has yet to be directly observed but is thought to make up a significant portion of the universe's mass. Cosmic strings are a fascinating example of how current theories in physics are being challenged by the discovery of exotic phenomena. The search for evidence of cosmic strings, along with other unusual phenomena, continues to push the boundaries of human knowledge. In addition to cosmic strings, the study of other enigmatic objects, such as dark energy, which is believed to be responsible for the accelerated expansion of the universe, is an ongoing challenge for cosmologists. As new technologies and more advanced telescopes come online, it is possible that these elusive cosmic objects and their associated phenomena will one day be detected and understood. Perhaps one of the most visually spectacular and scientifically significant phenomena in the universe is the supernova. A supernova is an enormous explosion that occurs at the end of a star's us to measure their distance from Earth and, in turn, the rate of expansion of the universe. The aftermath of supernovae is also crucial to understanding the cosmic expansion dynamics. The energy released in these explosions creates shock waves that propagate through space, further influencing the behavior of surrounding gas and dust. These shock waves, combined with the new elements produced in the explosion, can trigger the formation of new stars, further contributing to the ongoing cycle of birth, death, and rebirth in the cosmos. Supernovae also leave behind remnants, such as neutron stars or black holes, which are some of the densest objects in the universe and offer additional insights into the properties of matter under extreme conditions. The study of cosmic events and exotic phenomena such as gamma-ray bursts, quasars, cosmic strings, and supernovae represents a pivotal area of scientific inquiry that is essential for advancing our understanding of the universe. These phenomena, which occur on scales far beyond our everyday experience, provide invaluable insights into the fundamental workings of the cosmos, challenging existing theories while simultaneously opening up exciting new avenues for exploration. As we delve deeper into these cosmic occurrences, we begin to unlock some of the universe's most profound mysteries, drawing us closer to an understanding of both its origins and its potential future. Each of these exotic phenomena, whether observed as violent bursts of energy or intricate cosmic structures, contributes to the larger narrative of the universe's evolution. Gamma-ray bursts, for instance, represent some of the most powerful and energetic events in the universe, originating from the collapse of massive stars or the collision of compact objects. These bursts release more energy in a few seconds than our Sun will emit in its entire lifetime. By studying gamma-ray bursts, scientists are able to probe the extreme conditions that occur at the edges of stellar and galactic evolution, offering critical insights into the birth and death of stars, as well as the processes that drive the formation of black holes. Similarly, quasars, the bright, energetic cores of distant galaxies powered by supermassive black holes, serve as a cosmic laboratory for understanding the most extreme environments in the universe. The immense energy radiated by quasars allows astronomers to study the behaviors of matter under intense gravitational and electromagnetic forces. These objects, located billions of light-years away, also serve as probes into the early stages of the universe, providing a glimpse into the formation of galaxies and black holes just after the Big Bang. Quasars reveal how galaxies and their central black holes evolve, and by studying them, we can learn about the formation of the universe itself. Equally fascinating are cosmic strings, hypothetical one-dimensional objects that may have formed in the early universe during phase transitions. These strings, if they exist, could represent relics of the fundamental forces of nature before they separated into distinct interactions like gravity and electromagnetism. The potential discovery of cosmic strings could revolutionize our understanding of the fundamental structure of spacetime, providing key clues about the birth of the universe and the nature of the forces that shaped its earliest moments. Though they have not yet been directly detected, the study of cosmic strings offers new perspectives on cosmology, particularly in the context of the Big Bang and the inflationary period that followed it. Moreover, the study of supernovae, the explosive deaths of massive stars, offers profound insights into the life cycle of stars and the processes that drive the expansion of the universe. Supernovae are not just spectacular fireworks in the sky, they are also responsible for the creation of heavy elements, which are necessary for the formation of planets and, ultimately, life. By studying the aftermath of these powerful explosions, scientists can also investigate the dark energy that accelerates the expansion of the universe. Supernovae act as standard candles in cosmology, helping astronomers measure vast distances and unravel the mysteries of the universe's expansion. These cosmic events and exotic phenomena challenge existing theories, requiring scientists to rethink and refine our models of the universe. They push the boundaries of knowledge, inviting us to consider new possibilities and to expand our understanding of the fundamental forces and interactions that govern the cosmos. As we uncover more about these mysterious events, we begin to piece together the story of the universe's past, from its birth in the Big Bang to the formation of galaxies, stars, and planets. Yet, despite all the progress made in cosmology, these phenomena remind us of how much we still have to learn. Each discovery, whether it's observing the aftermath of a supernova or detecting the faint echo of a gamma-ray burst, brings us closer to unraveling the fundamental forces that govern the universe. By understanding these cosmic events, we gain a deeper insight into the workings of the cosmos, which in turn allows us to reflect on our own place within it. As we continue to study these phenomena, we are reminded that the universe is far from a static, unchanging entity. Instead, it is a dynamic and ever-evolving system, shaped by forces and events that operate on unimaginable scales. In a broader sense, the study of cosmic events and exotic phenomena has profound implications for humanity's future. As we continue to push the boundaries of space exploration and astronomical observation, we not only gain a deeper understanding of the universe but also unlock the potential for future discoveries. Technologies developed for studying these events, from space telescopes like Hubble to advanced particle detectors, have far-reaching applications beyond astronomy, influencing fields such as materials science, communication technology, and even medicine. Each new insight into the nature of the cosmos has the potential to inspire technological advancements that could benefit society in unexpected ways. In the quest to understand the universe and our place within it, the role of technology cannot be overstated. The advancement of cutting-edge instruments and techniques has expanded our ability to explore the cosmos, revealing secrets that were once beyond our reach. As technology continues to evolve, so too does our understanding of the vast expanse that surrounds us. From sophisticated telescopes that peer deep into the distant past to artificial intelligence, AI, that accelerates scientific discovery, the tools and methodologies at our disposal are revolutionizing the way we observe, analyze, and comprehend the universe. The future of space exploration is not only driven by these innovations but also by ambitious missions and international collaborations that aim to push the boundaries of human knowledge to new frontiers. One of the most significant breakthroughs in astronomical observation has come from the development of advanced telescopes, such as the James Webb Space Telescope, JWST. Launched on December 25, 2021, the JWST is the most powerful space telescope ever created, designed to observe the universe in infrared light. This capability allows it to peer through cosmic dust clouds and observe distant galaxies and stars that were previously hidden from view. Unlike its predecessor, the Hubble Space Telescope, which primarily observes ultraviolet and visible light, the JWST opens up a new realm of exploration by detecting wavelengths of light that are emitted by the earliest and most distant objects in the universe. The JWST's ability to observe these distant objects is crucial for studying the early stages of cosmic history. By looking at the light emitted by galaxies that formed only a few 100 million years after the Big Bang, the JWST will provide insight into the formation and evolution of the universe. Its observations are expected to help answer fundamental questions about how galaxies, stars, and planets formed, as well as the conditions that existed in the early universe. This could provide new clues about the origins of life and the nature of dark matter and dark energy, which remain some of the greatest mysteries in modern cosmology. In addition to optical telescopes, radio astronomy has become an indispensable tool for exploring the cosmos. Radio telescopes, such as the Arecibo Observatory, which tragically collapsed in 2020, and the Square Kilometre Array, SKA, are capable of detecting low-frequency radio waves emitted by distant cosmic objects. These waves offer a unique perspective on the universe, as they can pass through dense interstellar dust that might obscure visible light observations. Radio astronomy has played a key role in discoveries such as the detection of pulsars and the observation of cosmic microwave background radiation, which is a relic from the early universe. These technologies allow scientists to probe the universe in ways that optical telescopes cannot, revealing phenomena such as the magnetic fields of distant galaxies, the structure of neutron stars, and even the presence of exoplanets. Another groundbreaking development in space exploration has been the detection of gravitational waves. These ripples in spacetime were first predicted by Albert Einstein in 1915 as part of his theory of general relativity, but it wasn't until 2015 that scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, successfully detected them for the first time. Gravitational waves are generated by massive objects, such as colliding black holes or neutron stars, and they carry information about these events that can't be obtained through conventional light-based observations. The detection of gravitational waves has opened up a new era in astrophysics, allowing scientists to study cosmic phenomena through a completely different lens. These waves provide insights into the most violent and energetic events in the universe, including the mergers of black holes, the collapse of stars, and the birth of neutron stars. As the technology used to detect and study these phenomena improves, the accuracy and sensitivity of gravitational wave detectors will continue to increase. Future upgrades to LIGO and other observatories, such as the Virgo collaboration in Europe and the proposed Einstein telescope, will enhance our ability to detect fainter signals and study even more distant cosmic events. The detection of gravitational waves has already led to groundbreaking discoveries, including the identification of a kilonova, a type of explosion caused by the merger of two neutron stars. This discovery also confirmed that these events are responsible for creating heavy elements like gold and platinum, thus deepening our understanding of the origins of some of the universe's most valuable materials. The integration of artificial intelligence, AI, and machine learning into space exploration is revolutionizing how scientists analyze data. The sheer volume of data generated by telescopes, satellites, and other instruments is overwhelming, and traditional methods of analysis are no longer sufficient. AI algorithms are now being used to process vast amounts of information, identifying patterns and anomalies that would be impossible for human researchers to detect on their own. For example, AI is being employed to detect exoplanets by analyzing the tiny dips in light caused by a planet passing in front of its star. Machine learning algorithms can also help classify galaxies, identify supernovae, and predict the behavior of cosmic objects based on historical data. One of the most exciting aspects of AI in space exploration is its potential to accelerate discoveries. By automating data analysis, AI can help scientists identify new cosmic phenomena more quickly, opening up new areas of research and enabling faster progress in understanding the universe. AI is also being used to enhance the accuracy of predictions, such as estimating the likelihood of finding habitable planets or predicting the paths of asteroids that may pose a threat to Earth. The use of AI is transforming the way we conduct space research, making it more efficient and precise. As technology advances, one of the most ambitious goals in space exploration is the concept of faster-than-light, FTL, travel. Currently, the fastest spacecraft ever built, such as NASA's Parker Solar Probe, travels at speeds of up to 700,000 km per hour, but this is still a tiny fraction of the speed of light. However, scientists and engineers are exploring theoretical concepts that could one day make interstellar travel possible. One such concept is the Alcubierre drive, which is based on the idea of contracting space in front of a spacecraft and expanding it behind, effectively creating a warp bubble that moves faster than the speed of light without violating the laws of relativity. While the technology to achieve FTL travel remains purely theoretical and faces enormous challenges, the very idea has sparked imagination and driven innovation in propulsion systems. Another area of research is the development of nuclear propulsion technologies, which could potentially allow spacecraft to travel much faster than current chemical rockets. The idea behind nuclear propulsion is to harness the energy released by nuclear reactions to generate thrust, providing a much higher efficiency and speed compared to conventional methods. Proposals for nuclear thermal and nuclear electric propulsion systems are already being explored by organizations like NASA and SpaceX, with the goal of enabling faster and more efficient missions to distant planets, moons, and asteroids. While these technologies are still in the early stages of development, they represent a promising step forward in humanity's quest for deep space exploration. Looking further into the future, the prospect of interstellar exploration hinges on our ability to develop new propulsion technologies and overcome the vast distances between stars. Missions to even the nearest star systems, such as Alpha Centauri, would take thousands of years using current propulsion methods. However, by developing FDR travel or advanced propulsion systems, humanity could eventually venture beyond the solar system and explore exoplanets in other star systems, potentially discovering new habitable worlds. The rapid advancement of technologies, such as the James Webb Space Telescope, radio astronomy, gravitational wave detection, AI, and emerging propulsion systems is setting the stage for a new era of space exploration. As these technologies continue to evolve, they will provide deeper insights into the mysteries of the universe and open up new possibilities for interstellar exploration. The future of space exploration is bright, filled with boundless opportunities for discovery and innovation. As humanity continues to reach for the stars, our understanding of the cosmos will expand, bringing us ever closer to answering the fundamental questions about the nature of the universe and our place within it. We'd love to hear your thoughts about this video in the comments below. If you found this exploration of cosmic events and exotic phenomena intriguing, don't forget to like, share, and subscribe for more captivating content.